We've spent a lot of time talking about how human activities like farming or building cities can have big impacts on Earth systems. But this isn't just a doom and gloom story. Humans are also incredibly good at solving problems. This standard, HS-ESS3-4, is all about that next step. It's about being an engineer. We're going to look at the solutions we've designed to reduce our impacts, things like new energy sources or waste management plans, and learn how to formally evaluate them. It's not enough to have a solution. We have to know if it's a good one. First, let's get one thing straight. When we say technological solution, your mind probably jumps to robots or fancy computers. But in engineering, technology is much broader. It's any tool, system, or process that humans design to meet a need. A new type of solar panel is technology, absolutely. But so is a new farming technique like crop rotation. A citywide recycling program is a systemic technology. Even a new law, like the Clean Air Act, is a kind of social technology. Designed to solve a problem. All of these are human-designed solutions we can evaluate. So how do we evaluate a solution? We can't just say, I like it or I don't like it. We have to be objective. To do that, we need a scorecard. That scorecard has two main categories, criteria and constraints. Criteria are the goals. It's the what the solution must do. Think of it as the grading rubric. For example, if the problem is a polluted river, a criterion for a new water filter might be it must remove 90% of all lead and mercury. If it only removes 50%, it fails to meet the criteria. Constraints are the limitations. These are the must-nots. It's the box you have to work inside. The most common constraint is cost. It must cost less than $1 million. But constraints can also be time. It must be finished in 6 months. Materials. We can only use locally sourced parts, or even public opinion. Here is the single most important concept for this standard. There is no such thing as a perfect solution. Every single technological fix, no matter how good, has a downside. This is called a trade-off. It's the compromise. Think about a wind turbine. The pro is fantastic. It generates 100% clean electricity. That's what you gain. But what do you give up? The cons are that it takes up land, can be a hazard to birds, and some people think it's ugly. A trade-off is deciding if the pro is worth the con. Our job as scientists and engineers is to analyze these trade-offs honestly. This whole process of judging and improving solutions is called the engineering design loop. It's a cycle that scientists and engineers use every day. First, you define the problem. Be specific, like our city's landfill is 95% full. Then, you brainstorm solutions. Build a new landfill, start a recycling program, build an incinerator. Then you pick one, design and test it. Maybe you run a small pilot program for recycling. This is where you get data. Then, you evaluate that data. Did our recycling program meet its criteria, reduce landfill waste by 20%? Did it stay within its constraints, cost? And finally, based on that data, you refine it. It only reduced waste by 10%. Why? Let's improve the public education part and try again. This loop is how we make progress. Let's run a real-world problem through that loop. The problem: burning coal for electricity. This is one of the biggest impacts humans have. It affects the atmosphere by releasing CO2 and sulfur dioxide, which causes acid rain. It affects the geosphere through strip mining, which literally removes mountains. And it affects the hydrosphere when that acid rain pollutes rivers and lakes. This is a complex problem. Let's look at an early solution. In the 1970s, the big problem was acid rain, which was killing forests and fish. The specific problem was sulfur dioxide, or SO2. So engineers developed a scrubber. This is a huge device, sometimes the size of a building, attached to a smokestack. It basically gives the smoke a shower with a chemical mixture. This mixture reacts with the SO2 gas and captures it, turning it into a solid waste. This is a great example of a targeted technological fix. Now let's evaluate the scrubber using our scorecard. The criterion was remove 90% of the sulfur. And it does. It's very successful at that. So check. But what about the constraints? Well, it's very expensive, and it actually uses a lot of the electricity the plant is making, which is a big limitation. And the trade-offs? The pro is a massive reduction in acid rain, a huge win for the hydrosphere and biosphere. But the cons? First, it does absolutely nothing to stop CO2. It doesn't fix climate change at all. Second, it creates a new problem, tons of chemical sludge that has to be buried in a special landfill. So, we traded an air pollution problem for a solid waste problem. Because the scrubber didn't solve the whole problem, especially CO2, we had to refine our solution. This led to solution B, solar panels. This is a different kind of solution. Instead of cleaning the dirty source, it replaces it with a clean one. The technology is simple at its core. A photovoltaic cell is made of a material, usually silicon, that literally knocks electrons loose when sunlight hits it. Those moving electrons are an electric current. No smoke, no moving parts, no fuel. Let's evaluate this solution. The criterion might be it must replace our 100 megawatt coal plant. The constraints might be we can't build on the nearby wildlife preserve. Now, the trade-offs. The pros are huge. Zero CO2, zero SO2. It solves both acid rain and climate change in one go. But it has major cons. To generate that much power, you need a massive amount of land. Acres and acres of it. That's a new impact on the geosphere and biosphere. It's also intermittent. It doesn't work at night. And a big one. Manufacturing the panels themselves requires energy and creates toxic chemical waste. Again, there is no perfect solution. We just have to decide if this set of trade-offs is better than the coal plants. Let's try another one. The problem: feeding a growing population. Our traditional farming method is flood irrigation. We literally flood the whole field with water. It's simple, but it's incredibly wasteful. The impacts are huge. First, we waste tons of water, draining rivers and aquifers, the geosphere, faster than they can refill. Second, all that extra water runs off the field, carrying all the fertilizer and pesticides with it. This runoff pollutes the hydrosphere, leading to algae blooms and dead zones in the ocean where nothing can live. So engineers designed a solution: drip irrigation. This is a great example of a smart technology. Instead of flooding a field, you run a series of pipes or tubes across the surface with tiny holes in them. These holes drip a small, precise amount of water directly onto the roots of each individual plant. The best part is that you can mix a tiny, precise amount of fertilizer into that water. This is called fertigation. You're giving the plant exactly what it needs. Exactly where it needs it and when it needs it. Let's evaluate drip irrigation. The criteria for success: use at least 30% less water and don't hurt the crop yield. It passes with flying colors. It can use up to 90% less water and often increases crop yield because the plants aren't stressed. The constraint is money. It has a high upfront cost to install all those pipes. And the trade-offs? The pros are obvious: massive water conservation and a huge reduction in fertilizer pollution, which protects our rivers. The cons? It's expensive, and all those plastic tubes eventually wear out and become a new plastic waste problem. But if you compare the pros and cons, this is an A+ solution. Let's look at one final problem: our trash, or what I call the stuff problem. We live in a linear economy. We take raw materials from the geosphere. We make something. We use it once and we throw it in a hole in the ground, a landfill. The impacts are obvious. We're creating mountains of garbage. In the geosphere, we have to keep digging new holes for landfills and mining new materials. In the hydrosphere, these landfills can leak a toxic garbage juice called leachate, which poisons our groundwater. And of course, plastics are choking our oceans. Our first pass solution was to make a better hole in the ground. This is a sanitary landfill. This is a true piece of engineering. It's not just a pit. A modern landfill is designed to contain the waste. It has multiple liners, like dense clay and thick plastic, to stop leaks. It has a system of pipes to collect that toxic leachate, so we can pump it out and treat it at a water treatment plant. It's a high-tech containment system. Now, let's evaluate this landfill. The criterion is safely contain waste and prevent groundwater pollution. It does this very well. The constraint is location. Nobody wants to live near one, a problem called NIMBY, or not in my backyard. The trade-offs? The pro is that it does protect the hydrosphere from leachate, which is a massive improvement over an old dump. But the cons are huge. It's just a storage unit. It doesn't solve the waste problem. It just delays it. And it takes up an enormous amount of land that can't be used for anything else. It's a solution, but not a great one. This is where we refine the solution. The landfill is a linear solution. A better, more refined idea is the circular economy. This is a systemic technology. The goal is to design a system where there is no waste at all. Instead of take, make, waste, the loop is reduce, reuse, recycle. You reduce what you use in the first place. You reuse things, like a refillable water bottle, as much as possible. And finally, you recycle the raw materials, turning that old plastic bottle back into a new plastic bottle, closing the loop. Let's evaluate the circular economy. The criteria are reduce landfill waste by 90% and reduce mining of new materials. The constraints are massive. It's not a simple machine. It requires everyone in society to participate. It's also very complex. A single greasy pizza box can contaminate an entire batch of recycled cardboard. The trade-offs? The pro is a gigantic reduction in our impact on all Earth systems. Less mining, less pollution, less landfill. The con is that it's difficult, and recycling itself still uses energy and can create its own waste products. But just like drip irrigation, this is a much better set of trade-offs than the original solution. This brings us to the last part of the standard, refining. Refining is just the process of making a solution better, and it's driven by data. Look at solar panels. The very first ones in the 1950s were only 6% efficient. They were evaluated, and they failed to meet the criteria for powering a house. So engineers refined the design. They used new materials, new manufacturing processes. Now, the ones you can buy today are over 20% efficient. That is the engineering design loop in action. We have to monitor the performance of our solutions to get the data we need to make them better. So to sum up HS-ESS3-4, this standard is about thinking like an engineer. It's not just about identifying problems, but about critically evaluating the solutions. For any solution, whether it's a scrubber, a solar panel, or a recycling program, you have to be a skeptic. You must ask, does it work? Criteria. What are the limits? Constraints. And most importantly, what's the catch? The trade-offs. Our world is complex. There are no perfect answers, only better ones. Your job is to learn how to find them.